Hello, I'm Aditya Pandita, and today I'm going to speak on the topic of computing a texture feature using loss filters. Loss filters are basically a classical texture analysis method in computer vision, which uses a small set of hand-designed convolution kernels and produces a feature vector describing local texture at every pixel. Today, we are going to talk about where these filters come from, how they are built, how they turn into a usable per pixel descriptor. Next, next is like where exactly uh, our our talk exactly sits in the picture of our entire course. So prior to this, we have covered 2D discrete convolution and separable filters, standard filter toolkit that includes Gaussian, Sobel, Laplacian, median, and bilateral filters. And we have also covered why a texture must be measured over an area and not over individual pixels. Next, in today's talk, we will be covering loss filters, and this would further lead down into upcoming topics of Gabor filters, K-means, Verma's isomer filters, and VZ plain pixel versions. Okay, so for today's talk, we have five primary one-day kernels, which are derived from one idea that is, start with a smoothing kernel, then apply successive differencing to reveal finer details. So in these 1D primitives, we would be covering, whether those kernels are symmetric or anti-symmetric, and also whether the sum of those kernels leads to a zero or a non-zero value. First in this picture is an L5 kernel, which, if you, as you can see, 14641 is this basically represents how binomial coefficients appear in a series. And it also is a bit similar to a discrete Gaussian. If we see here, the sum of all of these values sums up to a non-zero value, that is 16. My bad. Yeah, this all sums up to a non-zero value, that is 16. It sums up to a non-zero value, that is 16. And this is the only kernel that responds to a flat constant brightness. And which basically means it measures brightness and not textures like our other 1D kernels. And a type of it would be used as a later used as a normalizer, that is L1 and L. Got the issue. This sums up to 16. Yeah. So this is symmetric and non-zero. Okay. Next one which we have is E5, that is edge. The values here, as we can see, are -1, -2, 0, 2, and 1. And as we can see from the shape of it, the first half is basically the opposite of the second half, and it totals up to 0. So what that basically means is it responds to non-flat patches. And it reacts strongly to a brightness edge, that is like on an edge, one side would be much brighter than the other side. And the sign of this kernel would also help us in determining what direction that edge is leading to. And it is filter similar to a Sobel filter. And if we see, this is an anti-symmetric kernel, and it sums to 0. Next one which we have is S5, also known as spot. Its values are -1, 0, 2, 0, and -1. Again, this is a symmetric kernel, which is symmetric around the center, something like a Laplacian operator. And, it's zero on flat regions and it fires strongly on isolated bright dark spots. So, which basically says that, yeah, this is something we use for spot detection. It's to zero. And as it is used for detection, it does not really respond well to edges or directions. It is basically direction blind and it responds to blobs and not to edges orientations. Okay, then we have our next kernel, that is a wave kernel. Its values are -1, 2, 0, -1, 2, and 1. And by the shape of it, we can see um, this is not a symmetric kernel again. This is anti-symmetric. And it also sums to 0. So, this wave kernel fires on signals that go up and down compared to, whether they are in a directional way or not. It is a higher order asymmetric edge detector. So basically an upgrade on E5. Next one which we have is R5. Um, Again, if by the shape of it, this is symmetric. It sums to 0. And this is used for, more finer, higher frequency filters in the set. It picks up, rapid pixel to pixel alteration, like some kind of patterns or static. So these are our five 1D primitive kernels, which we are going to use as baseline for our filters. Okay. Uh, Next we have building 2D filters via an outer product. So what this slide basically says or talks about is the mechanism or outer product of two 1D kernels. It's the same separability idea from earlier separability filters. And one example for it would be E5 transposed and multiplied with an L5 filter to get an E5 L5 filter. So this would act as an horizontal edge detector. E5 does the edge detection in one direction and L5 smooths the other direction here. And middle rows is all zeros because E5's middle value is 0. And signs here flips negative above and positive below. It comes from the E5's antisymmetry. The key relationships to note here would be E5, L5, and L5, 5, E5 are transposes of each other. Same pattern rotated at 90 degrees. One detects horizontal edges, the other detects vertical edges. And it sets up the merging step in the next slide. Yeah. So in the next slide, we would be discussing, various versions of the, L5 and E5 combinations. Not L5, E5 combination, but, 1D, 5 1D cross 5 1D combinations here. So As you can see here, this appears to be a matrix multiplication of the of our filters, and in the combinations here, these appear to be the same combinations. It's just a different way of applying the same combinations. So yeah, in total, right now it gives us 25 different filters, but by their use case, they kind of, uh, five diagonal ones here would be unique pairs, which are totally different, but the rest of the pairs which we can see here, they are basically, they contain the same kernels in them. And so the rest 20 pairs can be combined to make 10 merge pairs and 5 unique diagonal filters. So it gives us 15 unique filters. Yeah, and we can use these filters. Okay. Next, coming to, computing the feature at a pixel level. From filters to a per pixel feature, we'll see how that goes. So our step one here is convolve, which applies all 14 texture filters plus L5 to the image and derives 15 raw filter responses per pixel. Our step two normalize, it divides each of those 14 texture responses by L5 response at the pixel level. L5 is basically local brightness, which then goes into dividing mixed texture response invariant to the illumination. That is, a brightness versus shade values. Our step three here is measuring energy. That is, considering texture as an area phenomenon, not as a single pixel. It sums the absolute value of the response over a local window. That is, for example, 15 cross 15 pixel, and generates a stable local energy value. And finally, is our you know optional refinement as an histogram, which basically, takes instead of one energy number per filter, it builds a histogram of responses within the window. That is, for example, if there are 8 winds across 14 filters, it captures distribution shape and, not only just average magnitude. The result, you know, every pixel gets a 14 value scorecard and which feeds into a classifier or a segmentation algorithm. And next is a slide where we can see an example of a brick versus grass. So here in the bricks, you can see strong, regular, straight edges, lines between brick slash mortar, where we can expect a higher edge score on for an edge filter here. Grass, thin blades in many direction, fine detail, expected high score on wave slash ripple filters. And yeah. Then in the caveat, we can see numbers are illustrative, not measured from real data, but made up to demonstrate the concept. So yeah, so as you can see, bricks has separations in here, so it responds strongly compared to the grass and other filters. So this would be edges. That is an E5 filter. And there is no spot here, no edge here, they would respond as strongly. It can be saved as waves and ripples. Okay, next is slide 8, where we can see a real world example data from satellite imagery. The source for this was Aurora's vision documentation, and the subject here is satellite image of circular pivot irrigation crop fields. So in the original image here, you can see circular fields plus grid of roads between them. And in the filters output, you can see, The level plus wave, when you apply it to the original image, in here you can see not the edges, but some kind of wave at level features in there. And in the spot plus edge, you can see the middle, uh, some kind of blobs which are in there, and in the edge as well. And in the spot plus river, you can see dense, finer woven looking patterns across the image. Which is something, which we can also verify from the bar charts which we saw here. Um, okay. If in the 1980s, when this technology or when this algorithm came about, we have loss filters, and now in today's day we have CNN convolution layers, which does the same job. And finally, we can conclude that texture requires a neighborhood, not a single pixel. Loss filters, there are five hand-designed 1D kernels: level, edge, spot, wave, and ripple. Outer product of these five kernels lead to 25 separate 2D kernels, out of which there are 14 plus one distinct kernels. Symmetry collapses this to 14 genuine texture filters plus one average filters. Uh, the same thing. And pipeline per pixel is normalized by average filter, major local energy of histogram, which is in a stable descriptor. And from the result, we can see a per pixel feature vector useful for texture classification and segmentation. Uh, uh, this is what leads to or can act as a or acts as a direct ancestor of what we have learned in convolution layers. Thank you.